So in this video we'll look at how to implement the randomized complete block design in R, and the data that we'll use is the same data from the last video where we looked at R code for the completely randomized design. And if you recall, that data was about treating different plants with different fertilizers and then measuring their height to see whether the fertilizer treatment was effective in increasing plant height. And if you recall in that example, there was a blocking factor in the data set and we ignored it for that example, but now we're going to reintroduce it. So we could think about the blocking factor as something like the position on the bench in this greenhouse where the plants are positioned. And it might be the case that different amounts of sunlight fall on different rows in this greenhouse, and so we might want to take that information into account because the plants really aren't homogeneous with respect to height, right? Different plants at different light levels will grow taller or shorter. So we want to try to control for that factor in some way. And if you recall, the research questions that we were trying to answer were: are there differences among treatment groups? And is there a difference between level 1 of the treatment and level 3 of the treatment? And so here's the code to run a block design. And this shouldn't be surprising, right? It looks like the same sort of code that you would use for a two-way Anova, except we're interpreting one of the factors as a blocking factor and the other one as a treatment. And if you recall, this treatment factor had 4 different levels, a control, and 3 different fertilizer treatments, and the blocking factor had 6 different blocks for the different rows in the greenhouse. So we run our linear model, which, if these things are stored as factors, which they are, you'll have an Anova model, and we print out both a summary of this randomized complete block design and an Anova table, which we just studied in the last video. So by now you should be able to interpret this table. We've done it several times, both for one-way Anova and, in this case, for two-way Anova. And so what we'll focus on in this video is the Anova table down here. So the Anova function that I have highlighted here is what prints this table down here. And this is exactly the table that we studied and started to write down what these quantities were in the last video. So the main thing that I want us to understand, and this is to reiterate from the last video, that we're testing 2 different null hypotheses against 2 different alternatives. So the first null hypothesis is that we have the most basic model that includes neither factor, neither the block nor the treatment. And the alternative, if you decide to reject the null, is that we have a slightly more complicated model, one with just the blocking factor. And that p-value for this test here is given here. And so it's small on any account, whatever your alpha is, that's probably lower than it. And so you would reject the null hypothesis, and you would say, well, I at least need the blocking factor, right? And this test is not super important because we wouldn't have included the blocking factor. We wouldn't have recorded the position on the bench if we didn't think that it played some role. So the fact that we're saying it's statistically significant should not be too surprising. Now again, just a sense of how to get this p-value. Remember, the F statistic is what allows you to calculate this p-value. So you would use the F distribution and calculate under the null hypothesis what's the probability of getting an F at least as extreme as the one you got. And then this F statistic comes from the ratio of the mean squared errors. So this one divided by that one. All right, so what about the second p-value, this one here? Well, the hypothesis test associated with this p-value is given in number 2 down here. So the null hypothesis would be that you should have the blocking factor but not the treatment factor. And then the alternative would be that you have the blocking and the treatment factor. And so including the treatment factor here says that yes, there is some difference across the treatments, right? So some fertilizer treatment or the control does better with respect to plant height than some other. And of course this p-value is very small, and so we would reject the null hypothesis and conclude that the treatment factor is playing some role in explaining variation. So we saw when we studied contrasts that this, of course, is not the only hypothesis that's important, that there's just some difference among treatments. And so we could, again, use contrast here to try to compare different levels of the treatments or different combinations. And so we'll do the same thing, right? Since our research question above was the second one, is there a difference between level 1 of the treatment and level 3 of the treatment? We can use a contrast to try to answer that question, again, in the context of the randomized complete block design. So in the last video, I gave you sort of the way to do this the long way, right? Actually computing all the quantities that you need to test the contrast. Here I'll just use the built-in R function. And using the built-in R function, we get a table. And in this table, this number should look familiar, right? This is the difference between the first treatment and the third treatment. And that should be the same whether you have the blocks included or not. But one thing that I want you to do is compare the rest of these values. Compare these values to the table above in this code, which I've uploaded to Canvas, by the way. So you have access to this Jupyter notebook, and you also have access to the video, so you can just go back and check. But these values will be different than they were in the table above. And I want you to think, given the point of blocking, should the standard error term, for example, should this term be smaller or larger than in the table above? And is it in fact smaller or larger? So try to connect what your intuition says to what actually happens with this data set. And then notice that, well, I think the standard error will be different. You decide whether it should be smaller or larger. And then that will affect the t-value and the p-value. So I think it's a good idea to compare these two tables with and without the blocking factor so that you get a better understanding of why we're blocking to begin with. But the overall point here is to test the difference between level 1 and level 3, and this p-value does that. So this p-value is not very small, and so we would fail to reject the null hypothesis here, and the null hypothesis is that the two means are equal. So we don't detect statistically significant differences between these two treatments. And with that, I think we will stop. I leave you with these questions down here, comparing and contrasting the tables, which I think will be an important exercise, and maybe it's something that I'll include on the next exam. But we'll finish here with experimental design, and we'll move on to generalized linear models and generalized additive models after spring break.